Good morning, everybody. I'm Smruti Sarangi. So I'll be presenting slides from my second book. So my second book is published on advanced architecture. So you just kindly, you can go to my website and so from there, you will find a link to the book. So the
So,
print version,
Professor, there is something on the right hand side. I think is it the chart window open or something because it's showing the black on the right hand side.
oh, is it? Oh,
Yes,
sorry.
yes.
Okay, is it gone now?
Yeah, it is now it's a rectangular small yeah, now it is gone. And there is something on the top, but I think it's a zoom one.
No, that's the
That
Zoom one.
yeah, that will go away after that. Yeah.
That
Okay,
I
thank
don't
you.
think I have control.
Yeah, yeah.
Okay. So basically, the book is available. The draft chapters, they are available for free to be read online, and they are there on the website of the book. So the book, pretty much, at least in its draft form, is fully free and fully accessible. All the slides are also more or less fully free and fully accessible. So towards the end of the lecture, I will post a link. And so basically, you can then access it from there. But I'll primarily be covering material from the last chapter, which is architectures for machine learning. And as I said, anytime, any doubt, kindly stop me right then and there. And so I'll not be able to see you because I just minimize the window. But you just unmute yourself and ask, right? And so basically, I would presume that you have a background on these things on in-order pipelines, C++, and parallel programming. So what we will do is we will quickly cover the basics of deep learning and CNNs, even though you would have covered it over the last 2-3 days. So that's the reason I'll just move through these slides in a hyper fast manner. But if you want to stop me, kindly do so, and then I will discuss that in greater detail. So basically, I will just maybe quickly take 10 minutes of your time and ensure that at least we are on the same page with regards to the terminology at least. And then we will see, given a CNN algorithm, which is by far the most popular machine learning algorithm, how do we map it to hardware, right? So as you know, any machine learning algorithm is basically a function estimator. There are inputs, there are outputs, there is a relationship between inputs and outputs. That relationship is not known, right? So the point is, this is a black box. So to go from inputs to outputs, we need a function, and this function has to be estimated. And this is estimated with a parameterized mechanism. Of course, if it is simple, you could do curve fitting. But if it is large, multidimensional, and non-linear, what you actually need is a universal approximator, where what you have is that you just change the parameters of the functions. It is like a master function, which takes a whole bunch of parameters. Many of these parameters actually determine the function itself. So you change some of these parameters, the function appears different to you. And then as you keep on tuning these parameters, and there could be millions of parameters actually, it starts resembling something quite similar to your input-output relationship that you actually wanted. So this is a universal approximator. And the key point is that it is tunable, right? A set of parameters can tune it, and it can make it capture both linear as well as nonlinear behavior. So regression is clearly an example, which I'm pretty sure all of you would be familiar. So basically, I'm not spending a lot of time here. And also support vector machines, SVMs. They are also another example, which I'm also sure all of you would be familiar with, where basically the idea is that if I want to separate the red points and the blue points, well, I just draw a line, but the fact is that they may not be separable, right? In a 2D plane, they may not be separable. So what I do is that I project them to a higher dimensional plane. In the higher dimensional plane, I draw a hyperplane which separates them. But again, I do not need the equation of the hyperplane per se. What I can do is that I can only collect the coordinates of the points that are the closest to the hyperplane, known as support vectors. And that will help me in establishing broadly the region that separates the red and blue points, right? So this is pretty much the state of the art that was there till the late 80s, early 90s. Even the neural networks were still there. But the point is we didn't have the computational capacity to run large neural networks, right? So neural networks are primarily based on this nonlinear model where you do the same thing, you create compute a dot product between the input vector and a weight vector, or the input matrix and a weight matrix, doesn't matter. Add a bias term and compute a nonlinear function. And you do this across, you do this several times. So this is basically the idea of a neural network. But it is just that take a look at these functions. So if you take a look at these functions, sorry, I hope my face is visible. The camera is sliding us slightly. Yeah, so you take a look at these functions. So these functions have exponential terms in them, and this is hard to compute. So e raised to the power minus x, how do you really compute? Well, this is something you need to think about it, because the advent of machine learning now has happened because of two reasons. So you need to understand the historical perspective. So back in 2010, there was a lot of cloud computing going on. So what happened? There were a lot of small machines, and then there was a lot of cloud computing. So a lot of data got generated. Now, more or less, the process of ITification of any industry is done, be it a manufacturing industry or consumer or retail. The process of adding IT to it and creating a website and so on, all of that is done. Now, there is a lot of data that has been generated. Given the fact that a lot of data has been generated, what do we do with it? Well, we data mine it, we learn it, and so on. That is why you are seeing ML. But it is not that, we didn't have data 20, 30 years ago, but we didn't have the computational resources and the storage capacity for actually processing them, and now we do. And why did we not have? Take a look at these. Computing e raised to the power minus x is hard. What you can do is you can have a lookup table where given x, right, given the value of x, you'll have an approximation of e raised to the power minus x stored. But fine, then you need to do one addition and one division, and that is expensive. So one key thing that came from a computational point of view, right? So from a computational point of view, a key thing that came was the ReLU function. Sorry, this is the x-axis, not the y-axis, not this. Which basically said that, look, fx is 0 when x is less than 0. It is x when x is greater than equal to 0. If this is used as this nonlinear unit, sorry, I should maybe be calling it gx. So if basically this is being used as the nonlinearity in our network, it'll be, number one, look, it's far easier to compute. It's very easy to compute. Finding if an integer is positive or negative is just a matter of checking its MSB, the sign bit. And no problem. If it is 1, you just convert everything to 0. Or if it is 0, which means the number is positive, you don't have to do anything, right? So number one, computationally, the ReLU function was created, which was shown to also be a universal approximator. And this did ease our life substantially. So as if we graph all three functions, you will see this is how ReLU increases. Doesn't matter insofar as it allows us to create a universal approximator. So traditionally in machine learning, computing the output of the XOR function was difficult, XOR, exclusive OR function. But the point is that exclusive OR, if let's say I want to compute the exclusive OR of A XOR B, so pretty so this can be very easily computed, right? So the thing is that we have a simple network where A and B compute A minus B, compute B minus A. ReLU them, if you will, add them, and here comes the output. Okay, as simple as that. So the XOR function, which is traditionally considered very hard to compute in a linear, because it's a nonlinear function, was very easy with the ReLU thing. But of course, things didn't end there. And then, of course, we started creating much bigger neural networks, right, with this basic idea. So, of course, previously, as I have argued, the hardware did not exist to process and run such large neural networks. So the hardware simply did not exist. There were no GPUs, there were no fast FPGA boards. All of these things were not there. The on-chip memory and off-chip storage space, both of them were limited. Once these came, so you need three things, right? The reason that you are seeing more of machine learning today than, let's say, 10 years ago is because all three things were missing. It is just that we only look at the third thing and not the first two. But well, the talk is to change that. The first two is you need faster computing. You need GPUs, FPGAs, faster CPUs, all of that is needed. These were not there, they are there now. You need on-chip and off-chip storage space. They were not there, they are there now. And you needed large data sets. You needed a market. So this market was not there, it is there now. So, you take everything. Amazon used to be a much smaller company. Now it's a much larger company. So the requirements for understanding customer behavior are much more, right? So you look at anything, so the sheer amount of data has increased. And because of that, there is a need to do more of data analysis and learning and mining and everything. So now let me come to the meat of the talk. So by the way, any doubts up till now? Anytime you have a doubt, please don't hesitate. And please just, quickly raise your hand and ask me a question. Okay, so if there are no doubts, so we will go into some basic terminology of a convolutional neural network. So basically the input to a functional unit, I will call that an IF map. And the output I will call an OF map. So IF map is an input feature map, which is typically in the case of a 2D CNN, a 2D matrix. And the output is an OF map, which typically in the case of a 2D CNN is a 2D matrix. A layer itself will have multiple functional units, right? So it is not as simple as this, right? We will see that a CNN layer is slightly more complex, but it doesn't matter. So basically, for a given CLN map, it will take in multiple IF maps and it will produce multiple OF maps. So given the fact that you people know what is a CNN, I'm not delving more into it. And I will, for the sake of simplicity, only consider 2D CNNs in the lecture. And the 2D CNN, each element of the matrix is a pixel. So that is a terminology that we'll use. Input feature map, output feature map, IF map, OF map, and pixels. So then, of course, we will have nonlinear layers, two kind, pooling and ReLU layers. So the pooling layers that we will have, which are computationally not a challenge, is that you break a 2D matrix into groups of K cross K pixel submatrices, and then you either compute the max or the average and replace it with a single value. So then the large matrix will get converted into a smaller matrix. Okay, so this is known as pooling. So the advantage of pooling is several. First is that it corrects small shifts in the image. So translational shifts it corrects. That is one advantage. The other is that it computes the ReLU function. The other is that it also kind of smooths out, removes all the high frequency components of the image. So for the ReLU layers, it computes the ReLU function for each pixel, as we have seen, to provide non-linearity. Then, of course, we have a fully connected layer where the idea is that the input to the fully connected layer is the full matrix of, it's basically a full matrix. So the matrix is vectorized. So it's a full vector. And what you compute is this traditional weight transpose times X plus B, where the key idea is this is the same as the original equation that we had seen, where you take a entire matrix, compute a dot product and add it. So this is the one that is the computationally the most expensive. See, if I were to summarize, there are 4 kinds of layers in a CNN. There is a convolution layer, which incidentally we have not talked about up till now. Then there is the fully connected layer. So both of these are linear layers. The fully connected layer is this, which is basically a dot product plus a bias term. And this is then sent to a nonlinear unit, of course. But the nonlinear unit could be fairly simple. And the convolution layer is something which we will see. And then, of course, there are 2 nonlinear layers, pooling and ReLU. And any neural network will have primarily these layers. And it could have more. And of course, the point is that at the end, we could have other kinds of nonlinearities also, right? So I'm not trying to get into that like softmax and so on. But the key point is that we will primarily have these 2 linear layers, linear, and these 2 nonlinear layers. Computationally speaking, pooling, ReLU, we don't really care. The fully connected layer is computationally heavy, but thankfully only one of the layers is a fully connected layer, right? So you cannot have many of these. So basically, that's why in a large neural network, even with 100 layers, typically only the last layer is fully connected. The rest of the layers are what are known as convolution layers, which we will see now. So the key insight for a convolution layer is that, look, if let's say I want to detect an animal like a cat. So what is a cat? So a cat is typically something that has, eyes and a nose and so on, and then a tail and 2 legs, right? So basically the point is that you need one learner to detect the legs, count the legs, one to detect the tail, one to detect the body of the cat, one to detect the face, one to detect the ears. Once you have done, you want to aggregate these smaller concepts into a bigger concept, which is the face, the belly, the legs. And then, okay, you'll figure out it's an animal. Well, what kind of animal? A small animal. Small animal, again, it could be a mouse, it could be a cat, it could be a dog, but it has a shorter tail than a mouse. Okay, it's not a mouse. Okay, it appears furry, right? Furry also a few choices, could be could be a mink, could be a cat, and a few choices of furry animals, right? And finally, after several layers, you will finally make your decision. No, it's a cat. So this is the key point. So now the question is that we would ideally like to have these fully connected layers, but they are computationally very difficult. So the reason that CNNs are such a big hit and they are so popular is primarily because they are very computationally efficient. So here is the core operation, which is known as a convolutional operation. So it is important that we memorize these terms a little bit because I'll be using them over and over and over again. So consider a matrix. Let it have H rows. H, the way you remember is H is for height, W is for width, H rows and W columns. At the H, small h Wth point, let us consider a small window. Let it be R cross S. The way you remember it is R is for rows. S doesn't stand for anything, but given that S is beside R, it must stand for columns. So R rows and S columns. Typically R is equal to S, so that this is known as the convolution window. So what we do is that we take this and we take another same sized matrix known as a filter. This filter is called a filter or a kernel. Use any name you want. We will use a filter. And then you compute a matrix dot product. So what is that? Well, that is nothing much. That is a term that I just made up to make your life easy. But the idea is that you just compute a term by term product pixel by pixel product, multiply this with this, multiply this with this with this, and then you essentially multiply them. So in this case, you will have 9 of these products. You add these products, you will get a sum. And then, so we will call this the IF map, this the filter. In the OF map, what you do is that the matrix dot product, which is again a term that I defined, okay, it doesn't exist. Even if it exists, it means something else. But for this sake of this discussion, it means exactly what I said. Sum of term by term products. I do that with the filter, and the HWH entry is the value of the matrix dot product. Okay, sum of the element wise products. I do this for every location. I do this for this location. I do it for everyone. So now you will ask me what happens at the edges and corners. Well, so at this point, of course, this will look like this, right? Well, edges and corners, nothing much. Assume that these elements which actually don't exist are zeros. Your job will become easy. So the filter, of course, remains the same. It is typically small. Either it's 3 cross 3, 5 cross 5. Typically, it's an odd number. And then you zero pad it. So the basic idea over here, if I have a small diagram, is like this, that you take in the input image. Okay, so typically, the CNN is done on image. Typically, you do it to, identify objects, right? Identify that a cat is a cat, dog is a dog, elephant is an elephant. So what you do is that you have alternate linear and nonlinear layers. You never have consecutive linear layers because it is equivalent to one large linear layer. So what you actually do is you take in your input image, you run it through a convolution. When you run it through a convolution, what happens is that, any one of these layers, essentially you take in KIF maps and you produce K dash OF maps, where K and K dash need not have any relationship. In this case, like you take one IF map, which is the original image, and then you produce K dash OF maps. As you can see, these are several, and these are many matrices, right? Fine, you do that. After that, I do a nonlinear transformation. Then I pull it. So when I pull it, you can see these things become smaller. Again, I send it to one more convolution layer. Again, you see I have many of these, right? And then again, what I do is I send them to another ReLU layer. So again, I have many of these. And finally, I compute the output. And the output, I have a fully connected layer, which provides me the final output. So the key point over here is that I create a large neural network. So this is a feed-forward network. Okay, it doesn't have back connections. But nothing stops me from having a back connection like this. Then, of course, this will not be a traditional CNN. It will become what is called an RNN. But I can have many such connections and I can play around with these. And instead of having 5 layers, 6 layers, I can have 100 layers as well. And these internal matrices can also be fairly large. So all of that, is perfectly doable if my problem requires. But this is the general structure of a network. ReLU and pooling computationally don't pose a challenge. Their computational overhead is less than 10%. The fully connected layer does pose a challenge, but since we have only one of it, typically towards the end, again, we don't care. Why don't we care? Well, the answer is simple. We don't care because, there is only one such layer, and even if it takes, slightly more time, it doesn't really hurt us. What actually hurts us and what we care about are these convolution layers, which typically take 80 to 90% of the overall time. And that is why all our attention is focused on these convolution layers. Okay. So basically now coming back, we will go through this complex equation. But prior to that, is this clear? Do you want to ask any question or do you have any query at this point of time? Okay, any queries, kindly ask me. And so basically this, let's not have a monologue. It's better to have a dialogue where any
Hello,
query or
sir.
any, yeah, please
Sir,
go ahead.
sir, can you just explain this particular procedure of 80 to 90% convolution time in terms of any kind of example that while
Hey,
doing
please
some
also,
complex?
please also introduce yourself. Also tell me what is your name and where are you from?
Sir, I'm Kumaresh Sharma from Guwahati University, sir.
I see. Okay, what is your question?
Sir, this 80 to 90% is time which is being taken during the convolution, this computational time. So
Right.
that amount of time, that is means if most of the time CPU time will be required more in this particular time convolution period, sir.
That's right.
Yes, sir. So suppose I am considering a real means, can you give some relate with some example? Suppose I am taking this one, so this amount of time will be required. Uh, can you explain? Means, can you give some idea about that one, sir? Actually,
Yeah, so I have an image. Okay.
okay, sir. Yeah.
I have an image of politicians.
Okay, sir.
I want to find out if it is Mr. Modi or Mr. Adityanath, right?
Yes, sir.
Or maybe it is my image.
Yes,
Even
sir.
I have political aspirations, right?
Yes, sir.
So,
Yes.
so assume I have. So it's my image. So what is the difference? So the
Mm.
first thing is that this is the image. Okay. And
Yes,
then
sir.
let's say, consider a female politician. Okay.
Mm.
So
Mm.
the first thing is that the convolution layer, so it depends. See, what happens is that we don't really understand exactly what they do, in the sense they get trained by an automatic process. But broadly, what is known is that the first few layers detect major features and then the later layers fine tune. This is something which is broadly known and accepted.
Mm.
So the first layers will basically, so the first layers may do an edge detection. So if, let's say, if it is a
Yes.
face with a
Mm.
beard like this,
Yes. Yes. Yeah.
so the first layers will basically work on, so sorry, I stand corrected. What I said is reverse. The first layers are the ones which detect minor features and the later layers aggregate it. I stand corrected. So if it is a man with a beard, so the first layers will basically do edge detection. So they will detect edges and they
Mm.
will sort of demarcate a region like that. So
Mm.
these will get captured over here and the non-linearity will further refine it, and the
Mm.
pooling will further, compress the information and remove the high frequency components.
Mm.
Gradually, what will happen is that you will sort of create these broad level features of a face, right? And
Mm.
a beard,
Yeah.
right? And maybe you may also detect things
Mm.
like spectacles.
Mm.
Okay.
Person is spectacle. Yeah.
Right. So there are three people, Mr. Modi, Mr. Adityanath, and me. So Mr. Adityanath doesn't wear spectacles, but both of us do. Me and the Prime Minister, both of us do. Now, if a spectacle is detected, it clearly cannot be Mr. Adityanath. So one option is gone. So towards the later layers, what will happen is that then it will come to the beard. I don't have a beard. So given the fact that I don't have a beard, then the thing is that the only option that is left is the Prime Minister. But let's say that, it is my image and I don't have a beard, then the only option that is left is me. So what you do is initially you see these small things like edges and so on. You aggregate them into larger concepts. And finally, at the level of the larger concepts, you make a decision, right?
Yes.
So basically the point is that this figuring out these concepts is done by the convolution layer. And the ReLU layer and the pooling layer, if I were to explain it very broadly, they ReLU adds a degree of non-linearity in the sense it discards useless features. Okay, so to speak, in a certain way.
Mm.
So, but as I said, a lot of meaning cannot be given to them because if you see, it's an automatic process, right?
Yes,
And
sir.
things internally don't really work in this fashion. Okay, they don't really work in the fashion of beards and spectacles and so on, but they broadly proceed along that direction, even though not exactly. Clear?
Yes, sir. Yes, sir. Yes, sir.
Yeah, any other question?
Uh, Hi, sir.
Yeah,
Sir, I'm
you
from
are?
I. Hello, sir. Sir, I'm Prateek from IIT Roorkee. Sir, just I want to know, sir, how it's working on the 1D signals, because
Same thing, 1D signal, same thing. So instead of a two-dimensional convolution, it's a one-dimensional convolution. So I will show it to you. You just give me 2 slides. I will show it to you how it works on 1D and 3D.
okay.
So yeah. Any more questions?
Hello, sir.
Yes, you are, and you are from?
Udaipur, Dr. M.K.
Okay.
Jain, Mohanlal Sughadia University.
Okay.
So I just want to know that the computation time taken in the convolution is around 90%. So probably that would have been identified by the profiling itself. Na? The
What is profiling?
profiling means at the time of execution, how much time is taken by each component.
Yeah, it is known. It is known that the convolution layers are the ones which take the maximum time.
Yes, sir.
So
Fine.
that is known, and that's why we try to optimize it.
Yes, sir. Fine, sir. Thank you.
So each convolution layer, broadly speaking, can be said like this. Okay, so basically it is important we understand this terminology over here. Each convolution layer takes as input CIF maps, capital C, where each one of them is called a channel. Okay, so each one of them is called a channel. So it's called CIF maps. It's called C channel. So every layer, right? Every layer takes C IF maps or C channels as input. They have the same dimension. H cross W, H is height and width, same dimension. Then we convolve them with CK filters, C multiplied with K, right? I'll tell you why. So we convolve them with CK filters, where each filter has dimension R cross S. And of course, the dimension of the IF map and OF map can be different, but in my example, it is not. And finally, we produce KOF maps. Okay, so that's the key idea. In this case, they are the same dimensions. The important point to understand is that for producing a single OF map, right, we are producing KOF maps. So to produce a single OF map, we need all C channels. All C channels are required to produce a single OF map, and every channel is convolved with its corresponding filter, because there are CK filters, right? So which basically means that you can sort of have a matrix of C channels and CIF maps and KOF maps, right? Where I'll use a channel and IF map interchangeably. So to produce a given OF map, I basically need to consider all the channels, and for every channel OF map pair, there is a unique filter. So I will use that. And then basically, so for every, let's say for the ith channel, there is a unique filter corresponding to it. I'll convolve both of them and somehow combine all the information to produce the OF map. So I hope this part is clear. If this part is clear, then everything else will automatically be clear. But I just want to ensure that this diagram, this mini diagramlet that I have drawn, this is clear. See, if this is clear, you'll automatically be able to understand this, that in any layer, I take CIF maps as input and CK filters and produce KOF maps. So we can meditate on this for a few seconds, but kindly do ask me and interrupt me right now if you are not able to understand this part.
Sir, good morning.
Good morning.
Sir, how we can modify, can we modify this convolution, ReLU, polling, and like, can we do some different combination of these?
You can do any combination you want. Whether it'll give you a good output or not, that I don't know. But the point is, never have two convolution layers consecutively because it doesn't make any sense. Two linear layers, one after the other, is tantamount to one linear layer. So never have two convolution layers consecutively. That doesn't make any sense. And the rest is fine. And the entire thing is configurable. If it is in software, it is fully configurable. If it is in hardware, then the weights are at least configurable. So we will come to that. I will give you a little bit of a flavor, but I want to kind of direct your attention to this part, that whether you are understanding this part or not, which is that we have every layer has CIF maps as input, CK filters. For generating the kth OF map, all the IF maps are required. Every IF map is convolved with its corresponding filter, and then the OF map is produced. How well we will look, we'll take a look at it, but I hope this part is clear. If not, kindly interrupt me now.
Professor, good morning. This is
Good morning.
this is Ramasubramaniam. I'm from Liba, Chennai. So my question is regards to not related to convolution. Essentially, I understand convolution is basically a kind of data reduction, right? Is there a role for kernels here? Because we are always thinking about reducing the dimension. How about increasing the dimension?
Convolution is not data reduction. So let me take you to the equation. We will see. So actually, by the way, Sumit, are you there? Somehow, I mean,
Yes.
These lines have somehow come on my screen. I have not drawn them.
Okay. I'll try to see.
Can they be removed?
Yeah. Usually there should be option to stop the annotation. So I'll just check it at my end.
Yeah, I think somebody with powers has annotated.
Yeah, I'll just check it. Let me give
if it can be de-annotated, it would be good.
Sure.
Or maybe should I stop the sharing and start again?
Yeah,
Will
that
get...
we can try that also.
Okay, hang on. Let me try that. Okay, the annotation is gone. Can you see the... Can you people see the screens?
Yes.
Okay,
yes.
Fantastic. So let me, clarify myself. Convolution is not data dimensionality reduction at all. It is this. Okay, so let us go through this equation in great detail. I stands for IF map. F stands for filter. So N stands for image. So N is the number of input images is N. Right, where an image this is a case of 2D, but you can easily extend this to 3D or 1D. That's not an issue. If you are not able to figure it out, kindly ask. So N is the symbol for the number of input images, and small n is the iterator. Okay. So for the nth image, so basically the filters are not a function of the image. Now, the idea is I want to generate the kth IF map. No problem. So for the nth image, you want to generate the kth IF map. What do? So what you do is I am specifically interested in generating all the values for the kth IF map. Kth IF maps pixels H, W. Right? H is the row axis, W is the column axis. So this is, mind you, this is a single pixel, okay? For the kth IF map or the nth image, this is a single pixel. This pixel is a summation. It's actually a triple summation, right? I wanted to say triple integral, but it's a triple summation. And so it's a triple summation of what? You consider all the input channels. So you consider all the input channels are IF maps. For each IF map, you consider a rectangle that is rooted at the position HW for each IF map. Then you go R rows and S columns, right? So you will see R and S over here, which are the iterators for the row and column of the filter size. And so you see basically iterate through this region, and for each one you compute an element-wise product with the filter. Which filter? So as I said, for every IF map, OF map pair, we have a unique filter. So a filter is a 4-dimensional array, but if I take the first 2 dimensions, K and C, then for every IF map, OF map pair, we have a unique filter. Fine. So these two cover that. So what we do is we take an RS size region in the IF map, and the size of the filter is also R cross S. And then we convolve both. Convolving both means what? We multiply them element by element and then we add them. This process of addition is done for every single IF map, and the entire thing is added. When you add up the entire thing, you get the value of the H, Wth pixel of the kth OF map. Needless to say, we consider a batch of n images, and each OF map is produced from capital C IF maps, and there is a separate filter for each IF map, OF map pair. So I would like to ensure that this equation is understood, because this is the mother equation of all convolutions. And needless to say, this is 2D. If this is 1D, instead of 2 iterators R and S, there will be a single iterator. If this is 3D, then along with RS, you will have an R, S, and T. So instead of like a triple summation, it will become a quadruple summation with one more summation over here. But the point is that doesn't matter. So typically 1D, 2D, and 3D are considered. But given that 2 is like a sweet spot between them, I've considered 2. But is this part clear of what exactly I'm trying to do? Kindly take a look at this equation. So kindly take a look at it. Any doubt, please ask. So the N is the number of input images. C is the number of IF maps or input channels. Capital K is the OF maps outputs. The dimension of each IF map or OF map is height cross width, H cross W, and dimensions of each filter are R cross S. So is this part clear?
Yeah. Hi, sir. How is
Yes.
it possible that KOF maps are produced?
Well, that is what I want to do. And as you can see, I have an equation that allows me to do it. Why I want to do is a separate issue, but for the sake of this equation, that is what I want to do. And you see that there is a way to do it, right?
Right, but you are doing element-wise multiplication. So, so I think we should get COF maps.
Why? Why COF maps? I mean, you take a look at this equation. You think this equation will not allow me to produce KOF maps? For every OF map, you draw an imaginary line here. This is the kth OF map. For every kth OF map, I consider all the IF maps that I have. For every OF map, IF map pair, I have a unique filter. So consider this as one unit, right?
Okay,
and then consider this as one unit. You take one region over here rooted at HW, and then the filter has the same size, and then you convolve them. What's the problem?
Okay, sir. Fine.
Fine. Is that fine? Right. So
Yeah,
all of you can see my screen, right?
Yes, sir, we can see.
Okay. So given the fact that we have seen this, I can easily convert this equation over here into a sequence of 7 loops. right? So this is the classic 7-loop structure of a CNN, where I consider all the input images, I consider all the outputs, consider all the input channels, right? N, K, then C, then H, W, R, S. And instead of having this equation over here, I just replace it with this summation over here. Which is nothing but exactly the same thing. NKHW, NCH plus R, W plus S, same thing. NKHW, NCH plus R, W plus S, KCRS, KCRS, exactly the same thing. Instead of an equation, I have lines of code with 7 loops. Correct? And each one of them is a partial product, and kindly appreciate the fact that the equation is the same as the 7 loops. And here is the fun part. These 7 loops can be reordered. You can just reorder them any way you want. You can take this fellow, put it at the top, bring this to the bottom, just reorder them any way you want. The computation remains exactly the same. Okay. So basically the most important question is that this loop is exactly the same as you just reorder this with that, no problem. So now here is the question. The question is, this is the typical hardware of a machine learning accelerator. Okay, so basically what is the hardware? We have a sea of computing elements where each computing element is very basic. It has a small amount of cache. This cache is known as the local buffer. It's like the L1 cache. The processing element is very basic, slightly more than a dignified ALU. The elements itself are connected in a matrix in an NOC. So you have rows and columns and so on. You have a global buffer, which is more like an L2 main memory. And then you have a task dispatcher, which coordinates the activities on this. And you have a main memory. So broadly speaking, this is the architecture of any hardware CNN unit. And nowadays, of course, CNN is becoming more hardware than software, but the basic architecture still remains the same. So the most important idea is that in this 7-loop structure that I showed, the loops can be reordered. Okay. The ordering is important not for correctness, but basically for performance. In the sense, different orderings have different degrees of performance. Okay. So the ordering is important because the cache accesses, the locality, everything is important. So it determines the cache behavior, network on-chip behavior, and so on. And furthermore, what we can do is that instead of a 7-loop structure, we can add more loops and we can tile the loops. This will help us control the locality. And I will show you in a second how we do that. So this was the classic 7-loop structure that you have seen. Let's just see what I did. Focus on this loop and this loop. Instead of incrementing by 1, I incremented by the tile size, which is TH and TW. So what I do is that I consider blocks of TH cross TW blocks, and I can compute my convolutions in them. So I have a 7 loops, and then I have 2 more loops where I iterate within the tile and I compute these partial products. So why do I do that? Or call them partial sums. Well, why do I do that? So the idea is that I can consider a chunk of data in one go. So this will increase and improve my cache locality. This is why I break down my input and output data into tiles. Okay. So this is known as tiles. Instead of a 1-1 tile, I have a TH cross TW tile. So what I can do is now I have a 9-loop structure instead of a 7-loop structure, where I have divided this into tiles. And now what I do is that this remains the same. It is only the iterator changes. So now I have 2 iterators for, let's say, H and W. H1, which is the tile index, and H2, which is the index, the real index. So instead of H1, I use H2, W2 everywhere. So did you understand tiling? So first question is question 1. Did you understand the 7 loop structure? Question 2, did you understand tiling? So if anybody has any doubts, kindly stop and interrupt and interject and interrogate me now.
So Professor Sarangi, so this is basically to reduce the number of memory read transaction from the cache memory, right? In the for loop. The tiling is used so that we can reuse the data multiple times before we send it back to the memory again.
Right.
Okay. Okay.
So, sir, what I understood was that we are using this tiling to reduce the number of data that is going to our local buffer in wherever we will be computing
Not
this.
reduce, well, it's not to reduce the data.
Mhm.
It is basically to increase the locality such that you can read a full chunk of data from main memory and increase the cache hit rate.
So instead of taking the whole of the data and computing it one by one, I am taking smaller chunks of data and then
Right.
computing.
Hmm.
Okay. So generally we have these channels are a bigger quantity. These rows and columns are bigger quantity. Won't you want to tile all these loops also? The channels.
I can tile
the rows?
any loop. So I'll show you a generic framework where I can tile any loop.
Okay.
So Steve, here is the main thing. We need a formal representation to specify the order of the loops, right? The order matters. Okay. The order matters not for correctness, but for performance. The order matters for performance. Yeah, any question? Then the tiling also matters again for performance. Also, the thing is that we may want to specify data locality in the sense we can keep some data like permanently cached within an LB. We can pin it to a local buffer. So we have two terms here, local buffer, global buffer, and then main memory. So we may say that, look, you keep something in the local buffer, you just keep it there. So this specifies the data locality. This is known as stationarity. But broadly speaking, these are the 3 knobs that we have. Okay. Okay. So now that we have seen this, so let us create a small representation such that we can map it to hardware. So if I have the 7 loop structure, which you have become experts by now, I can represent this. This will capture the sequential ordering of the loops. N, K, C, H, W, R, S, N, K, C, H, W, R, S. Right? One within the other. This is indicating a sequentiality. Are you clear? So this is the notation we will use. So now I will add some more additions to the notation. So if let's say that this is more like a postfix kind of notation where the operator comes after the iterator. So if I have the parallel symbol, it means we process all the images in parallel. If you have 2 such parallel symbols, H parallel, W parallel, this means we process all HW pairs in parallel. If we have a parallel and sequential symbol, this means you first process all the H elements in parallel. Then within each group, you process all the Ws in parallel. So first parallelize the loop with iterator H, and within each group, you parallelize all the Ws. Okay, so this is the parallel symbol. This is the sequential symbol. And if I have 2 such things, one after the other, it means that the entire group is parallelized. If I have a symbol like this, right? So it means that you first parallelize this, and then within each subgroup, you parallelize the rest. Then we have the symbols H dash and H double dash. So assume H is being tiled. H dash indicates the number of the tile, and H double dash indicates the number of the pixel. Okay. So H dash is the tile number and H double dash is the pixel number. So of course, when you are mapping this to P's, if we have more iterations in the number of P's, it will fold. In the sense, you first will consider one group and then the next group. So let us understand this. Let us understand our tiled execution. Our tiled execution, the one that I showed, this fellow, I have NKC, H tile, W tile, RS. So just see the way I do it. NKC, H tile, W tile, H dash, W dash, RS. And then I consider the pixels H dash and H dash dash and W dash dash. Is this clear? This is for tiling. So kindly meditate on this and tell me if you understand this or not till I take 2 sips of water. Any doubts, ladies and gentlemen?
Okay, sir. Now we are first inviting the our projected tile first, and then we are computing each pixel of that tile.
That's right.
Okay.
That's exactly right. Okay, so then it appears that you have no difficulty at all. Good. So now we have from first gear, we will go to second gear. But anybody else, any doubt? Just kindly shout. Now consider the following mapping. NKC parallel HWRS. What is this? We will see. So N means consider the images, then output IOF map, then C input IF map, NKC. But what is this thing? This basically means that you go image and output map wise, but you consider for each OF map, you consider all the input IF maps in parallel. This is exactly what it means. C1, C2, C3, and Cn. Okay, it's actually C capitals. All right, this is what you do. And then, of course, within for each channel, again, you perform a sequential computation. But the moment, what I mean with this RS shaded basically means that so RS is basically for the filter, right? This is when you're accessing the filter. So these accesses for within the filter, these you keep them cached in each local buffer. So the filter is cached in each local buffer, which means the filter is reused as much as possible. So these accesses which are made are actually made to the filter which is cached in the local buffer, and this you reuse as much as possible. So basically, is this mapping clear? The second one. So is this mapping clear? The fact is we consider the channels in parallel and we keep the filter cached. Is this clear?
But sir, if I want to keep, I want to have RNS value in the cache, shouldn't they be accessed parallelly?
No, it is being accessed parallelly. No. So in this case, it is not being accessed parallelly. If you want you to access parallelly, you'll have to change the equation. Right. So for this particular mapping, it is not being accessed parallelly. Right. If you want to do, then you will have to change the equation. So I'm only telling you what this representation is saying. What should be done is a separate matter. Okay. Get the point? I'm only trying to explain to you what is written, but I'm not saying it should be done. What should be done that is a totally separate issue. Now, right. So now let us understand a little bit of this fact of where we keep the filters stationary. If we want to reuse the filters as much as possible, so what is the filter really dependent on? it is dependent on the KC pair. Ideally, we should maximize the distance between KC and RS, right? Such that the moment we have set our KC, then our RS is fixed and then we can reuse the filter as much as possible. So we set the KC pair over here. We iterate through all the images, then iterate through all the tiles, of course, in parallel. So in this case, you're iterating through the tiles in parallel. And then basically we are iterating through all the pixels and doing our convolutions, right? So the tiling part is, tiles are being processed in parallel. But the key point is that we have maximized the distance between KC and RS to maximize filter reuse. The only problem is we'll have to reload our images many times, which is something we may not want. If we don't want that and we want to process one image at a time, then we can have the images over here. We can instead process an IF map, OF map pair in parallel. And for that, we can then sequentially look at, we can just sequentially perform the convolutions and we can still keep the filter cache. So this is one more mapping. Which mapping is more superior? Well, that's a separate issue. For that, you may have to do simulations. But the main idea is to teach you how the meaning of these mappings. I do hope that this part is getting increasingly clearer to you, the way that these mappings are supposed to be done. So any doubts with these two mappings? So you realize that if I want to, so this is known as a weight stationary mapping or a filter stationary mapping, where I'm trying to maximize the distance between KC and RS. And here the point is that I have managed to do it in the first mapping. But then if I don't want to reload input images, then I load an image once. I process all IF map and OF maps in parallel. In both cases, I keep the filter cached. So is this clear? Okay, you're not complaining, so I would believe it is clear. So it is, so once you get a hang of it, it will get quite simple, and I think many of you have. So what I will do, if you don't have any questions, if you have, at any point, kindly ask. If you don't have, I will move slightly further, and we will discuss a method to keep, instead of the filter stationary, the input stationary. So again, what we will do is we will only work in terms of these representations. So here also we process an image at a time. Then we process the tiles in parallel. This is what it means. Process the tiles in parallel. For a given tile, we will consider one OF map. And then what we will do is we will move through the filter weights. But here is what we will do. What we will do is that we will keep tiles for all the C channels cached within the local buffer. So this part will be cached within the local buffer. And of course, we can move RNS over here. No issues, no problems with that at all. But the point is that we will keep this cached within the local buffer. Okay. So in this case, what we are doing is we are keeping the input stationary. Get the point? The input is being kept stationary. And within the local buffer, the input is being kept stationary, and we are actually varying the rest. So in this case, what we are doing is that we have kept the input stationary, and the tiles otherwise are distributed across they are distributed. The tiles are distributed across the P's, the processing elements, but each P stores C tiles of input data, and it computes the convolutions. So of course, in this case, one finer point is that the size of each P, right? Number of columns should be TW plus W minus 1. You will ask why? Well, the point is that even though this is the real size of the tile, we may have to compute a convolution which is of this type. Okay, let's say for the corner element. So then where do we get the rest from? It is much better to consider a slightly larger chunk with overlaps, such that, the rest of the pixels don't have to come from the neighboring P. So that is why instead of the regular tile size, we store a slightly larger tile size over here. But this is again a finer point, and these extra pixels are known as halo pixels. So this is nonetheless a finer point. But is the key idea of this equation clear to you? So kindly look at this and ask me if there are any doubts.
Sir, won't that actually increase the memory requirement, because for like each for some of the input pixels we have to store them on multiple P's, right?
That will increase the memory requirement, no doubt. So see, I'm just discussing different paradigms, right? So input stationary is a paradigm, particularly you may prefer that. If, well, I don't know. I mean, see, this is hard, okay? It's very hard to reason why one. So we have discussed weight stationary or filter stationary, which had a different equation. We will discuss input stationaries. Input stationary, this problem is there that you mentioned. Okay, this is a problem. But of course, if the tile size is large and the filter size is small, it will not make that much of a difference. And there are also other ways of doing it, but this is definitely one of the ways that an input stationary thing can be done, but the input is kept fixed, right? So now we can also look at output stationary, which is the same thing. I just replace C and K. So it's the same thing. Again, consider it image by image, parallelize the tiles. Consider one input channel after the other. And then basically consider, so what you do is that each, for a given tile, right? So for a given output map style, you essentially store all the partial sums for a given tile. So this is something that is stored within the LB. This is something that is cached. So this is the same thing as it was for the input stationary thing, but of course, in this case, the connotation is different. Again, you have to take care of halo pixels. So basically, of course, that you'll have to take care all the time. But this is the key and broad idea. Get the point? So in this case, the output is being kept fixed, right? So the output is not being varied. The output is being kept fixed. And what is actually being varied is the input. So far, so good. Okay, so once that has been done, so another approach, this is a very different kind of approach. So look at this. This is a different kind of equation. So in this case, what we do is we just iterate through the images, the OF maps and IF maps, NKC, no parallelism over here. What we parallelize it is across the rows. So these are the rows of the IF map and the rows of the filter. H is the row of the IF map. R is the row of the filter. So essentially, we just parallelize it across the rows. So then what happens? And then what we actually keep static are actually the rows are the ones which are kept static. And so basically, we take a long row of an IF map. We take a short row of a filter. And then we just compute a 1D convolution at each P. Right? So this is exactly what it means. It's known as a row stationary architecture, which is quite popular. The reason it is quite popular is because a lot of very efficient hardware already exists to compute a 1D convolution, right? So that is the reason that it is so popular, that we can reuse that hardware, we can leverage that hardware to compute a 1D convolution. But essentially the parallelization that is happening is across the rows. And then we just distribute a row of the input and a row of the filter to each P. The P basically slides this filter along the row in this direction. It computes a set of partial sums, which are then, of course, aggregated to find the final value of the output tile. Right? So this aggregation is done. But is this idea clear of the row stationary architecture? So we have discussed 3 degrees of stationarity: weight or filter stationarity, input stationary, output stationary, and row stationary. So in this case, we keep different kinds of things cached. But these are the 4 things we discussed. Is this clear? Any questions that you would like to ask at this point?
Sir, I have a question, like how can we choose among those different these stationary models? Like, is there some intuitively we can see, okay, this might work better or that might not?
See, that is quite hard. Okay, you'll have to see if you have very efficient hardware for computing 1D convolutions, go for row station. So row stationary in general tools, there are tools like time loop, which basically will look at these 4 paradigms and tell you which one is the most efficient for your network. This also varies. This is a function of N and K and C. Capital N and K and C.
So for if we are working on an FPGA where we can decide how much hardware we want, so then I think the keeping the filter size stationary would be the best one.
Not necessarily. I mean,
because
some degree of simulation is required. In the experiments I've indicated for some inputs, OS is better, for some WS is better. It's not clear.
So I was saying this because I think the filters are all mostly the smallest ones in.
But then you will not benefit much by caching it.
Yes.
You will benefit much by keeping more data. It depends on the size of the cache, many things. So see, there are 2 kinds of reuse. Okay, coming to the hardware part. So we don't have a lot of time, but at least I would like to cover the first few slides.
Yes.
So the key idea is you load some data into the caches, the LBs, local buffers. The size of the local buffer is a variable. The power consumption is a variable. The other is spatial reuse. So moment I compute a partial output, right? What do I do with it? Do I keep it? Or do I discard it? Or do I move it around? Do I pass it around the P's, right? What do I do? So typically, if I have something, instead of writing it to memory and reading it once again, as far as possible, you move it around from P to P to P, which is something we will see. So there are 2 kinds of moving around. One is I broadcast it to the rest of the P's. I just, broadcast it and I say, all of you take it. The point with broadcast is it is easy to implement, but the thing is other P's might not require it at that point of time. Right? If you broadcast something, it may not be immediately useful. And also broadcasting has its own set of hardware challenges. For example, in FPGA, broadcasting is difficult. In the parcel where I send it to my neighbor sends it to its neighbor, so on and so forth. So that is systolic transfer. But now, of course, we'll slightly nuance it for hardware. So again, we'll consider it image by image. We will first divide the computation. We'll parallelize it by the output channel. But again, we'll parallelize it by the output channel first. So we break the columns into the output channels. And then we will parallelize it on the basis of the rows. So again, we will do the same. On the basis, the rows will be given to input channels. And then we will keep the filter weight stationary within the P's. So consider a single output channel K1, which is basically this column over here. And assume that there are 4 input channels, C1, C2, C3, C4. For each one of them, we broadcast the data. The corresponding filter weights are locally cached within these LBs. So you have all the information that is required to compute the temporary convolution of OK1 C1. And then this will compute, sorry, OK1 C4. This will compute OK1 C3, right? This fellow will compute OK1 C1. So pretty much all the partial sums are computed, right? So what you need to do is that you need to transfer the partial sum from this P to this P, they get added. Then the whatever you just added, again you transfer it over here, you add it over here, and again you transfer it over here, and finally you read it like this. So this is a systolic transfer, but finally what you are ending up doing is that you are computing the summation of OK, K1 actually, across all the input channels. So you are computing this summation, and finally you stream out the output via the bottom. So as you can see, your data is streaming in like this. And for a given column, you are actually computing the output, of course, for a given tile or for a given pixel, for a given output channel. You are adding up all of that, and what is coming out is coming out from the bottom for a given output channel, right? For a given OF map. So is that clear? So can you see, can you see how this equation is mapping to the actual hardware and how a systolic transfer is happening column wise? So let me erase all the ink such that you can see it much better. So can you see how it is happening?
Yes,
So
sir.
any doubts with this? Because this is really the crux. So if you think about it, right? So we have 6 minutes remaining, but I wanted to bring you till this point such that you can see how the equation would actually map to a hardware and to the computation. So this is it for the weight stationary computation, but can you see how it is happening? Any doubts with this? Because this slide is quite important. It is essentially showing you how the computation will actually be done. So what we do at the top is that we divide the set of columns. Then we again divide the set of rows into the IF maps. We stream in the data like that, stream in. So this data gets broadcasted along the row. And let's say for a given output channel K3, all of them compute a partial sum, and the partial sum is aggregated in this fashion. And finally, the data streams out like that. So any doubts with this? Anything that you don't understand with this diagram which you would like me to clarify?
So, sir, with this architecture, like we are using parallelism as well as the data, we are reusing the data again so that the memory accesses could be reduced and we can get an efficient architecture. Right?
Yeah. So then, if I look at the IS architecture again, which would be the same thing. Consider one image, parallelize the tiles. After you parallelize the tiles, what you do is consider for a single OF map. So then what you actually broadcast is, what you actually send is that you send the filter weights. And so the moment you send the filter weights, what each tile is going to have cached is basically the tiles for each of the input channels. So in this case, what you do is you broadcast the filter weights to every single tile. So as you can see, the filter weights are broadcast to every single tile. And here, what you have over here is that you have C input tiles basically, right? So the tiles are distributed. So you have you have all the tiles, for all the IF map tiles are there over here, convolution. And so there is no need for systolic aggregation. You can just stream the output out of this way. You can just stream it out. There is no reason or there is no need to do anything else at all. Get the point? So basically here, there is absolutely no need to do anything else at all. And so basically all that needs to be done is that the filter weights have to be broadcasted. Each one of them will catch it. It will perform all the convolutions locally. And finally, it will get the output weights, the outputs, so not the output weights, but the output OF maps out. Right? No addition, no aggregation has to be done. If we look at a slightly more efficient IS architecture, it could be like this. I consider each image. I consider the tiles again in parallel. Right? So I don't care about the tiles, but let's say they are assigned to the columns. I consider them in parallel. Then I again consider the channels in parallel, which is over here. So what I do is that for every tile, I just broadcast the, I just send the channel weights, and then I send the filter weights, right? So the pre-filled inputs is for a single IF map. It's not for more than one IF map. So one IF map is over here, right? Over here, and over here. And what I basically do is that once the filter weights are sent for a single output K, what I send is basically I send the filter weights, which are again captured by each one of them. And as we have seen in the first case, they are aggregated in a systolic fashion. So the partial sums are added up in a systolic fashion. Right? So this will be one more example, broadly speaking, of the IS architecture where the filter weights are added. So basically here, what we are essentially storing is that we are storing for channel C1, for instance, we are storing the IF map. For C2, we are storing the IF map. It is internally stored. So what we are sending is we are sending the filter weights. So of course, we have like prefixed that we are sending it for output K. So for output K and C1, we are actually sending the filter weights down this, we are broadcasting this way. Similarly, for K and C2, all the filter weights are being broadcasted this way. Each one of them is absorbing the filter weights into here and computing a partial sum. Once this has been done, right, for the same tile, all that you need to do is you need to aggregate them systolically. That is all that needs to be done. And after aggregating them, the final output comes out via this. So what you are basically seeing, so I would like to, maybe I'll give an overview of the books. I like to stop over here. But what you are basically seeing is that, look, we have a representation. So I'm not saying the representation is very accurate and exact, because it's not really possible for it to capture so much of information. But the point is, it does capture some information. And this information can lead you or can take you to designing a piece of hardware in this fashion. Okay, where you parallelize it first by the tiles, then you parallelize it by the channels. And then what you do is you send the filter weights. And then you perform the convolutions at each P and then aggregate it systolically. Is that clear? Is that understandable or understood? So any doubts over here? So I just wanted to do a quick, show you my book. But I mean, before I close the presentation, anything that you would like to ask regarding the representation, which I believe, given that you are asking questions, most of you have understood, and the way that this is being mapped to hardware. Any other questions you may want to ask? All right, so I'll do one thing. I will quickly just, maybe open the web browser, and I will show you, how to navigate to the material. So I'll share the screen. So all of you can see my web browser?
Yes, yes.
Yes.
So you go to my home page. Sorry. You go to my home page. All right. So in my homepage, so this is my book on undergraduate computer architecture. This is an advanced computer architecture. All you do is that you click this book. So the moment you do that, you will see links to all the draft chapters. So for example, a draft chapter on architectures for ML is over here. So you come here and then it will directly open the chapter itself in Dropbox. Right. So this is the chapter itself. So you can read the entire thing online. You can't download, but whatever I said, you can read it. After that, the slides are there for almost all of them is there. ML and so on is coming, but the slides are there and the YouTube videos are also there. So the slides and there's some chapters are missing, but all of that will come. So the slides and YouTube videos are all over here. And we have developed an architecture simulator for simulating many of these things that I showed. So a link to that is over here. It will take you to the homepage of the Tejas Architecture Simulator. So, so this is where I would like to stop. Anything else, kindly do ask me now. I'll turn off the sharing of the desktop.